Yeah, so for the module test, there'll be an integrity statement. You're in a professional college, so ethics, professional ethics is important in your profession. So we want you to take that seriously. We do monitor some, services, online services, and so if we find copies of the test there, we can figure out who put them there. So, and we have in the past taken academic action against those people. So try to do it, honestly and with integrity and on your own, and that will set you up better for your own, studies in the future. Okay, so assignment 1 is in. Assignment 2 is now available for you. There is the Physics 156 help desk on Tuesday evening. So the first one was last night, and it was nice to see somebody there. There are also first year engineering like help sessions, I think. I'm not sure, maybe you guys can help me, or you can help me. Are they targeted or are they open? Like, is every session open to any questions?
They have TAs there or professors, and you just join the Zoom and you get put in a breakout room. And sometimes they don't have all the TAs there, but we have a schedule.
Okay. We've been sending them our information, so they should hopefully know what's going on with the questions and the topics that you're covering. But the 156 session is on Tuesday evenings, right before it's before the assignments due on Wednesday morning. Okay.
Do you know where we find the schedule and join the Zoom calls?
For the Physics 156 help sessions, they are in the Zoom. What's it called? Is it Zoom schedule in Canvas? It says Zoom in the little menu option. It's down the left-hand column with the modules and the syllabus and all that stuff. There's a Zoom link, and in there it has the links to the labs as well as to the help session, and it comes up in order like of what's coming up next. So if you logged in yesterday afternoon, you would have seen the help session at the top of the list.
What about the general engineering ones?
That I don't know. It should be available to you through the engineering first year courses. Does anyone else know?
Sorry, it's in the GE 103 class Canvas course.
Okay.
It should be at the top, I think, of when you just open the modules.
Okay.
Great. Thanks everyone for helping each other out. I appreciate that.
I was wondering, with the group 10 having labs Tuesday nights, how does that work?
Yeah, that's a good point. What time is the lab on Tuesdays?
It usually starts at 5:30.
And goes till when?
Last one went till about 6:30.
Okay.
But when it goes in person, it might go later.
Yeah, like it's scheduled till 8 p.m.
Okay. Yeah, our help session is scheduled from 6 till 8. But if you have questions and that you want to connect in, please send me or any of your instructors a message, whoever's teaching at the time, and we can connect in and hang around longer and answer your questions for you.
I'm just wondering where we can see the assignment 2 link on Canvas.
I'm just making a note about the labs to tell the other instructors. Is it section 10 only that has Tuesday labs?
I'm pretty sure.
Okay. The assignment 2 link should be in the assignments tab. And then it should be available in WebAssign also. You should be able to see it in there. We've set them to be visible as of 9 o'clock this morning. Can you see them in there?
I can see the written solution portion of it, but not the WebAssign link for the assignment.
You can't see it on Canvas, but if you follow the assignment 1 link and then click
Mhm.
the assignment tab and
Oh,
send
here
gauge,
we
you can
go.
see it.
Okay, I just made it available now. Thank you. It looks like it doesn't have an opening date, so our available date automatically set. Should be there now.
Yeah,
It is.
thank you.
Great. Thank you. Thank you for helping everyone in the class. Okay. All right, let's go through a little bit of review here. Okay, so can anyone tell me when a positive charge is free to move in these, when a positive charge is free to move between these plates, we know that it moves away from the positive plate and towards the negative plate. So what happens to its potential energy as it goes from left to right?
It decreases.
Decreases, right. And what happens? Oh, it says here, the potential also decreases, okay, because it's potential energy per unit charge is the potential. So the positive charge moves from high voltage to low voltage, okay? So the positive charges move in the direction of the electric field. They move from high potential energy to lower potential energy. They lose potential energy and increase their kinetic energy because they're accelerated. And they also move from higher to lower voltage. Their voltage decreases or their potential decreases, okay? And potential is really literally the voltage that you talk about related to circuits, okay? We also looked at a negative charge. So the negative charge between these parallel plates will be repelled by the negative plate and attracted by the positive plate. Can anyone tell me what its potential energy does as it moves to the right here? Anybody
It would
know?
decrease, right?
Yeah, it decreases. It decreases. And the weird complication here is because it's a negative charge, the force and the electric field are in opposite directions. And you can see the force is sort of sketched out here, and the electric field is in the opposite direction from the positive to negative plate. And that confuses a lot of people because E is opposite to the direction for negative. So the delta U decreases, but it moves from the low voltage or low potential plate to the high potential plate. So because delta U, or sorry, because delta V is delta U per unit charge, when you put a negative charge in here, then delta V and delta U do the opposite thing. So for both charges, their potential energy will decrease because they're accelerating and their kinetic energy is increasing. But one of the charges will see a decrease in voltage, and one of the types of charges, the other type of charge, will see an increase in voltage or potential. And so we got here the memory tool. Positive charges roll downhill to lower potential. And it behaves the same for a positive charge behaves the same in the sense of it decreases in potential energy and it decreases in potential. But negative charges do two different things. They decrease in potential energy because they're increasing in kinetic energy, but they increase in voltage or potential. So the electron moves from the low plate to the high plate. So it moves from low to high potential, okay? So that's just something you gotta remember. And it's only because we're using these kind of field ideas. We've got potential energy per unit charge. So we imagine, the potential energy for whatever charge we put into that space. That's what the potential, kind of tells us. Okay. So I think I quickly rushed this, and I gotta correct something here. I think this is where we ended last day. We did potential, which is labeled the distance basically, or E dot ds integrated over the full path. In this case, because the path is a straight line and the electric field is a straight line, and they're they're parallel or anti-parallel. We had it becomes a simple multiplication for this distance here. Can you see something that I missed here last time? I was rushing, so that's what happens when you rush. Can you see something I might have missed here? We have a minus sign out front and a minus sign out front, but E is this way and ds is this way. What happens when you dot things like that? Anybody know what happens when you do E dot this distance D when they're opposite?
Does it change if they're like IJ? Is that K now?
It does change, but it doesn't involve a new dimension.
A negative sign?
What's that?
Theta will be 180.
Yeah, the angle between them is 180. So you end up with a minus times the magnitudes. Okay. A dot B is equal to AB cos the angle between them, right? Did you learn this in your math class just recently? like this week? Anyway.
Last week.
This week, okay. This is so brutal. Oh, I apologize on behalf of the program. So if E and D are parallel, it's a straight up multiplication. But if E and D are anti-parallel, it's a multiplication, but with a minus sign. The dot product gives you the projection of one vector in the direction of another vector. And when they're completely opposite, then the projection is in like the negative the direction of the first vector. Okay. So what I should have had here was another minus sign with some absolute values. So this actually turns into a plus CD with these being magnitudes. Okay. Because the electron moves, it rolls uphill. So it moves from lower to higher potential. Okay.
What direction is D? Is that just a distance?
D is the displacement of the particle along its trajectory where it's feeling the force. So the electric field is to the left. The force is to the right because it's an electron. It's being forced away from the negative plate to the positive plate. Okay, so we have a force acting in this direction and this distance D in this direction as well. Okay. That makes sense? So D is this scalar distance, but the path of the electron is a vector to the right. Okay. Okay. Everybody okay?
Yep.
Okay, thank you. Okay, so this question asks us to find the speed of the electron as it exits the accelerator. So let's do that. Okay, so let's think of things we know. We have the electric field. I think we're told what it is. told what it is. Oh no, we're doing this in terms of variables. We're going to derive this. So we have an electric field between plates. We know that the force has to be in the direction like parallel or anti-parallel to the electric field, and they're related by this expression. But it generally, force is also equal to mass times acceleration. Okay, so we've got two relationships there. We know that work is equal to force times the displacement. And in this case, we'll use we won't be using the little differential parts because force is a straight line, distance is a straight line, so it's just a multiplication here. All the vectors are straight and parallel or anti-parallel. We also know that work is equal to the change in kinetic energy, and that's equal to minus the change in potential energy. So we know all of these relationships. We also know that delta V is delta U over Q. Okay, so for generic Q. So these are all the formulas that we have to work with here. Okay, so we're going to eventually want to get here to this term with the acceleration because we want to find the velocity, right? If you were given this question by the way on a test, you'd be given a little bit more information. We're just going to walk through this so that you can kind of think about this and how you might solve this given, you know, a specific question, okay? So the work done, so we have our plates minus plus, we have our negative charge, we have the electric field going this way, we have the force going this way, and we have a displacement here between the plates. Okay, so we've got these vectors that we know. Work is equal to force times distance. Okay. Okay. But force is QE dot your displacement vector D. We have an electron, and that charge is equal to minus E. Okay, that's the electron. And this is minus E. Let's make this the X direction. Okay, does that make sense? So we've got two minuses here. So we've got work is equal to minus E times minus electric field E times D, magnitude, okay? So going forward, let's make the symbol E without the vector sign just equal to the magnitude of E, okay? Two minuses cross out or cancel out, we get E times E, force times distance. Is everybody okay there? The change in potential energy is minus W. So it's minus E times the electric field due to the distance between the plates. Okay. I'm going to change the page here.
Could you just one second.
Yeah. Yeah, take a snapshot of that. Okay, is everyone following along? There's lots of minuses. That's why electrons are a pain in our necks, because you got to be very careful about the minus signs, because you've got minus charge, and then you've got E in the, like, usually in the minus direction or the opposite direction of the force. So that's where things get a little hairy. You got to be really consistent. Go ahead. Anybody still waiting there? I don't hear anybody.
Why are we letting
No.
E equal the absolute value of E for that one?
Yeah, because when we do the E dot D, we do this. We do E dot D. So we have magnitude of E times X hat, but it's in the minus direction, and D is in the X hat direction. I don't know if you can see that. So we end up with, if we do minus X hat times E magnitude times, or dotted with D times X hat, we get minus E times D, and X hat dot X hat is 1. Okay, so we've taken the direction out and put it in, we've explicitly written it so that now when we just write E as the letter, it's just the magnitude, because we've explicitly accounted for the minus X direction by putting a minus sign in. Does that make sense? So E, the variable, is just a number, a positive number, and the minus sign for the minus direction here, minus X direction, has already been taken out. We've dealt with it.
So then at the
Is that okay?
bottom in that circled formula, is that negative sign out front from the capital E, or is that one from the lowercase e?
That is from all of them. That is from all of them. We have a minus from the equation. We had a minus from the charge E. We put in a minus E as the charge, where this is just, E is just a number. So it's, the charge of an electron is minus 1.6 times 10 to the minus 19 coulombs. So E is equal to 1.6 times 10 to the minus 19 coulombs. It's just the, the kind of atomic charge, or the charge of a proton or electron, the magnitude of it. Okay, so we've got the minus sign in this equation down here. We've taken into account minus E, where E is 1.6 times minus positive number. All this line for this E with the dot products, we've got 3 minus signs here. This is why things get confusing. So we have 3 minus signs, and we end up with an overall minus. And then this E is just a number, a positive number. This is just a positive number, and this is just a positive number. We've pulled out all the relevant minus signs and multiplied them out, and we end up with a minus in the end. And then these are just numbers. Does that make sense?
Yeah, that makes sense.
Yeah. And if you look at this, when the thing moves, when the electron is free to move, it should move in the direction of decreasing potential energy. The potential energy should drop while it's being accelerated by the electric force. So if these are all numbers with no minus signs, these are all magnitudes or positive numbers. The minus sign out here tells us, oh, we're right, because we should get something that decreases. The change in U should be negative number, because it should be dropping, right? You don't have to do it this way, but if you are not consistent with dealing with your minus signs, when you go to plug things in at the end, you'll have, various minus signs extra, or not enough of them or something in the end, and you're probably a sign error at the end. To use absolute values of our symbols, magnitudes of our symbols, and then pull the minuses out if we know them. Okay.
So if this was a proton, the electric field would be positive, and the small e would, or I guess it wouldn't be a small e in that case, because it wouldn't be an electron, but we wouldn't have any negatives, right?
We only have the negative in this equation down here. This is the only one we would have. So E dot D, E would be in the plus X direction and D would be in the plus X direction. So that dot product comes out with plus E times D. And then the charge of a proton here is plus E, where E is just the number, like E is the magnitude. So it would be a plus here as well.
Okay, yeah, that makes sense.
Okay, so you'd have
Also,
where you do the yeah.
I
Yeah.
don't know if it's just
And-
me, but your cursor might be also frozen.
Oh, I keep forgetting that it freezes in here. My apologies. I'll try to draw stuff.
So we
this
know
charge
that.
here,
Sorry, we know that the E
Go ahead.
is in the negative X direction because of the positioning of the plates, correct? Because that the positive plate is on the right. And that's just kind of because we defined the negative or the positive X direction going to the right, correct? Okay, thank you. Sorry about that.
correct. Yeah. Yeah, no problem. If we, it doesn't matter how you choose your coordinate system, so long as you're consistent. In the end, we want the acceleration or the velocity of this negative charge to the right here. So I chose plus X to be to the right because that gives us a positive velocity vector and positive acceleration. It's in line with the motion of the charge. But there's no right answer there. Or there's no right way to choose your coordinates. I mean, you could choose plus X to be in the minus direction, but it's not typical. And I've just chosen this, so it kind of helps us in the end.
And so that's just from the theory that we know that positives are the electric force always goes away from the positives and to the negatives. So if the plates were switched opposite directions, the field would be positive.
Yep. And you can see it here where we had a positive charge example. So here the electric field is to the right, from the positive plate to the negative plate. And in this case, the force and the electric field are in the same direction, so we don't get this weird minus thing going on with the negative charge and then the anti-parallel E and D and all that stuff.
Thank you so much.
Yeah, you're welcome. Thank you for the questions, everybody.
One more question.
I appreciate it. Yep, go ahead.
What if we were to reverse the coordinate direction we chose for X and Y?
You would have a negative D and you would have a positive E if you reverse the X direction. Right now, we have a negative E and a positive D, and if you reverse the X direction, you'd have a positive E and a negative D, so that dot product would still give you a minus E times D. Like the combination of those two gives you this same thing.
Oh, okay. All right. Cool. Thanks.
Yeah, and when you keep all of their symbols constant, regardless of the direction, the potential energy should still drop when the charge is free to move with the electric force. And it's not a vector, so the potential energy and the work shouldn't have a sign related to the coordinate system. The sign should be related to the energy level of the particle as it moves through that force field. Okay.
Are we only going to deal with parallel plates like this question? Or is there going to be instances where the dot product isn't just the multiplication of the two values?
Yeah, we're going to do a little bit more relating the electric field and the potential today. So we'll get to some different examples later today. Okay. But I tried to scale back the math quite a bit. So mostly what I want you to really concentrate on understanding is, the direction of the force relative to the electric field for positive and negative charges, the change of potential energy and the change of the potential for positive and negative charges, kind of understand what those mean, right? What we're trying to make it so that the math isn't the thing that trips you up. Like if you understand the concepts, you'll get most of the marks. That's how we're trying to set it up. Hopefully we get it close to a good thing, but yeah. We're gonna do point charges later. So I'll rewrite this. delta U is equal to minus E, little e times big E times D, where these are all magnitudes. They're just positive numbers. Okay, delta V is delta U per Q. I'm going to put this that we had before up here, and then replace Q by the charge of an electron, which is minus 1.6 times 10 to the minus 19 coulombs. Okay, so again, this is just a number. And this is just a number. We've taken the minus sign out and written it explicitly. So we cancel those out. And we cancel out the E's. So we get delta V is equal to E times D, which those are all magnitudes. So this delta V is positive. Okay, so the final potential is higher than the initial potential. Delta means final minus initial, remember? So if this is a positive number, it means the final potential is higher than the initial potential. Okay. And again, electrons roll up the potential hill. Okay. Not how you might intuitively think things work, but that's how it works for electrons. If we did this for a proton, we would have a minus E times D. Because protons do a little bit more like when a proton's potential energy decreases, its potential also decreases. But this minus sign of the electron means that when the potential energy of an electron decreases, its potential increases, the V increases. Okay. It just, that minus sign for the potential just means a proton and electron get accelerated in opposite directions. Okay. I'm gonna go to the next page.
Sorry, what does the V stand for again?
Potential. It's potential energy per unit charge.
Oh, okay.
It's kind of like a potential energy field, if you want to think about it that way. If you put a charge in a region of voltage, you know, a region of known voltage, you can tell which way a positive or negative charge will move, because it always moves to region to, you know, in the direction of lower potential energy. So if you have a region of V, like a map of V that you know, then you can tell that a positive charge will move one way and the negative charge will move the other way in a voltage field or potential field. Okay, so delta U is potential energy and delta V is potential. That's what it's called. Okay. And potential is literally voltage like you'd see in a circuit or in your, you know, in your, you know, on your light bulb or on your, you know, computer plug-in cord or whatever. Okay.
So just to get this clear, like electrons move towards a positive potential?
It moves to a region of higher potential, yeah.
Higher potential.
Yeah.
Okay.
Yeah. And that's actually something that brings up a point that's really important. So thanks for asking that question here. As you can see, we've just got deltas here. There's no such thing as an absolute voltage value or absolute potential value. The only thing that's important is the difference, because it's related to the work done by the force over, you know, across some displacement. So only the difference is important. So it doesn't matter where you put the zero potential or the zero voltage. So you may be in a region of entirely negative potential values. So, but the electron will always move to a higher potential, even if it's just a less negative potential, if that makes sense. So it's not necessarily a positive potential, it's just an increase in the potential relative to where it started. Okay. And a proton moves to a lower potential. Okay, now find the speed, not the velocity. So energy conservation tells us that whatever potential energy change, there will be a change in the kinetic energy, but with the opposite sign. So if we lose potential energy, we increase in kinetic energy. And you know this hopefully from like dropping a ball. At the top of the trajectory where you drop it, it has a lot of potential energy, and as it falls, it loses potential energy, but it gains kinetic energy, it gains speed. Okay, so here again, we have to keep track of the sign. So we have minus, and then our potential energy change was minus E times capital E times D. And again, these are all just numbers, positive numbers. And delta K is 1/2 mv f squared. The initial velocity is 0. Okay. So if you rearrange this, you get the square root of 2 times little e times big E times the displacement or the distance between the plates, and then the mass. I should say this is the mass of an electron. Okay, so if you had some numbers to plug in, you plug them in there. Oh, okay. Everybody good?
So then a proton would be the same thing, except the mass would change and it would be in the it would be a negative value.
The mass, you're right that the mass, like if we had a proton in this question, the mass of the proton would be here, right? But the velocity is still the same sign because we would have had to set the question up with the plates in the opposite direction. So our minus signs, like we'd have E in the plus X direction, we'd have D in the plus X direction, and so on. So the minus signs, there'd be no minus little e, because Q is just equal to E for a proton. So the minus signs work out to give you the same answer. And this would be a good question for you to try and work through at home, like do the same thing for a proton and have the plates reversed. So a proton is released next to the positive plate. What is the final speed when it reaches the negative plate? And you should, you should get the same answer with the same sign. Drop my stylus on the floor. Okay.
So how do we avoid getting confused between the velocity and the potential?
Yeah, good question. The potential of the voltage is always written as a capital V. And you'll even see it on your devices. You'll see like 1.5 volts with a capital V. And then I use a lowercase or kind of a script V for the speed or the velocity vector.
Okay.
Yeah. Yeah, we have a lot of variables. Like even here, this is a distance, but sometimes it's a little differential thing like a dA or a ds. So I worried about giving you this as a letter D. It's just a distance here though. So it just depends on the question that you're working on. Okay.
So if we had a question like this on the test, we wouldn't have this VF equation. We just have the beginning stuff and we'd have to derive it and then solve it.
Yeah, I can't remember. If you look at the formula sheet that's posted, you may have kinematic equations on there. I can't remember. It may be up on the right hand side up at the top, maybe. I haven't looked at it since it was posted, but we would ask you to, we would expect you to know this, I think, because you've taken the kinematics course. Did you take this? Kinetic energy is equal to 1/2 mv squared. Have you taken that before?
Yes.
Yeah, okay, yeah. And I think it's on the formula sheet, and there's some like A times x minus x0 is equal to V times, whatever those equations are for kinematics. There's a few of those there too, I think. So we would ask you to do this using equations on the formula sheet or combinations of equations in the formula sheet where you can get to where you need to go. Okay.
So the velocity is a scalar quantity in this case, and in the x-hat direction is a vector, right?
The question asked for the speed. So this is the magnitude of the velocity. But according to the schematic or the diagram, we know that it's in the plus x direction here to the right. So the final velocity is in the plus x direction. So if you wanted to write this as a vector, you would put a vector over the f and then put an x hat. But the question just asked for the speed, which is the magnitude. Okay, so let's move on here. Here's where we get to a little bit more complicated version of this. So if we have a point charge, we can find the potential due to a point charge or the potential difference due to a particle moving near a point charge, because we know what the electric field of a point charge is. We know what that equation is. It's you've done it on assignment 1. It's KQ over R squared in the radial direction. Oh, Meave, I think your mic's on.
Sorry.
That's okay. It sounds like there's some kind of like Avengers type battle happening where you
My chair is really squeaky.
Oh no. Okay, thanks. Okay. So we're going to do a quick derivation here of how you find the potential, the equation for the potential of a point charge. And what's going to happen is we're going to substitute, KEQ over R squared into here and do this little integral. One thing that's important again is that there's no absolute voltage or absolute potential anywhere. So we need to choose a place that we set to 0. So what we do for point charges is we say, let's choose the potential to be 0 at an infinitely large distance, because that's a convenient place, because any particle that you put out there would be very, very far from a source charge. So we wouldn't expect for the particle to feel any electric force out there. So that's kind of a good place to set a 0 voltage or a 0 potential. Okay, so the electric field and the electric force falls off to 0 as you go to infinity. So let's set V equals 0 out there. Okay. Okay. So we are going to put a charge here. We know that for the electric field of a point charge is a spherically symmetric thing. So we'll know that the electric field is in the direction of the radial vector, and then at any particular radius, the electric field is the same. So what's going to happen is we're going to be out here at infinity, and then we'll set that to be V equals 0, and then we're going to bring a charge in to this distance R and figure out what the potential difference is from infinity to this distance. Okay, so this will be our initial, and this will be our final position. So we're moving in the radial direction from infinity, where we've set V equals to 0, to this distance from the point charge that's at a distance of radius R. Does that make sense? So delta V is the difference between the final potential minus the initial potential. So we move a charge in from infinity to a position near a point charge at radius R. So if we set the reference, like the initial point or the reference, to 0, then we can talk about a potential as a function of R, V as a function of R, or a point charge. Okay. All right. So the next thing we've got to do is know that this is a function of r in the radial direction. And then dr oh, minus r here. We have here. Hang on. Moving from infinity. Yeah. So we have r times r hat. And that's our final position. Okay. Is that right? I'm confusing myself now because we're coming in from infinity, but you can't put infinity in here because that will. Oh, I know why. I know why. Okay. I think we have a minus r here now. So E is equal to KEQ over r squared, r hat. So in the radial direction. So the r squared and the r will cancel out here. Oh, I lied. I'm confusing all of you. Let's start again. Let's start again. Let's get rid of this because this is confusing. I'm confusing myself. Okay. Delta V equals VB minus VA. So we're going from infinity to some position R. Delta V is equal to minus the integral from infinity to position R, E dot ds. One second. About that. So we are going to replace this with dr as a variable, and then we'll set the direction using the limits of our integral. So this is something you'll be learning about a little bit more, I think, in your math class. So forget what I just told you. We could just have a differential length ds or dr, and E will be pointed in some radial direction also, but we're going to run this integral from infinity to r. So we'll do, when we do the integral, we'll have the value at infinity substituted in first, and then subtract the outcome of the integral with the value of r. So we have minus the integral from infinity to r of kq over r squared dr. And we run from infinity to r. So the direction of this integral is defined here. The integral of 1 over, like dr over r squared, is minus 1 over r. And we run it from infinity to r. Okay, so we have KEQ over r minus KEQ, and this isn't really mathematically correct to write this, but when you substitute infinity in there, in the denominator, that term goes to 0. Okay, so that's the reason why we set like that. We've set our potential to be 0 at infinity, and it works out here. Does that make sense?
What happened to the negative in front of the integral?
When you do the integral of dr over r squared, it's minus 1 over r. There's a minus in the
okay,
integral.
I see. Yeah, so
Yeah,
you just
'cause it's-
canceled it.
Yeah, exactly. Yeah. Thanks. Okay. Everybody ready to go next page? So V of R of a point charge is KEQ over R, and it's a scalar. It's not a vector. So for any radial distance, the voltage or the potential of a point charge is a constant. So you'll end up with, lines of constant potential around a point charge. Okay.
Sorry, but how is V of R KQ over R? Because in the previous slide you wrote the potential difference is V to infinity minus V of R. So if V infinity goes to 0, then the potential difference is minus VR.
No, it's V. You substitute first in, we've integrated from infinity to R. So when you do the substitution of the limits in your integration, you put the final term in first. So it's final minus initial. Okay. So it's
Yeah, I get that, but like on the first line, you have the potential is V infinity minus VR.
Oh, yeah, okay. Yeah, that's wrong. Thank you. This is VR minus V infinity. So this is VF minus VI. Thank you. Thank you.
Wait, where is that we have to change?
Sorry, I didn't get that.
Where is that mistake we have to change?
It's right here. It's just this term here. I had infinity minus R, and it should be R minus infinity. VR minus V infinity.
Oh, okay, thank you.
Yeah, because we're doing final minus initial. Oops, we're doing final minus initial, and we start out at infinity, and we end up at the final position of VR in this calculation.
Sorry, where did the negative sign from in front of the integral go?
When you do 1 over, or if you do dr over r squared, it's minus 1 over r. That's the integral. So if you take the derivative of minus 1 over r, it turns into plus 1 over r squared. The minus sign was in the integration and canceled out. Okay. Okay. Oh man, we're so far behind. Okay. So we've got this equation now. This is equal to KE. It's another way of writing it. So if you have a point charge of capital Q and you're at some position P, which is a radial distance R, the potential at that point, we call it KEQ over R, and it's a scalar. Okay. So when you do a calculation of the potential due to more than one point charge, you calculate KQ2 over R2 plus KQ1 over R1 magnitude, like the distance, plus KQ3 over R3. So you do this, and it's a simple addition. There's no vectors here. This is the reason it's a really useful tool. It's the reason why we like potential, because it's just numbers, not vectors like forces and electric fields. It's a straight up addition. You don't need components. Okay. Okay. So we'll do an example. Given a negative charge of -6 microcoulombs and a positive charge of 2 microcoulombs, they ask us to find the potential at a point P here on the x-axis, and then figure out how much energy, potential energy, it would take to bring in a third charge from infinity to this point. Okay, Remember that delta V is equal to delta U over Q. So if you know the potential here, and you know the potential at infinity, which is 0, you can figure out how much energy it would take to put a third charge at this location. How much energy would be needed, or how much work, or negative of work, I guess, to bring a charge from infinity and place it there, because you're moving that charge through an electric field and putting it there, or moving it through a kind of a potential energy field and putting it there. Okay. So let's do that. So we've got point P, we've got Q2, we've got Q1 minus 6 microcoulombs, we've got 2 microcoulombs, we've got this distance. We're told that this is 3 meters, this is 4 meters. For Pythagoras' theorem, we know that there's such a thing as a 3, 4, 5 triangle, so the hypotenuse has to be 5 meters. You would do that calculation, but I'll leave it up to you, like if you did it in your homework. This would be R1, the distance from Q1 to P, and this is the distance between Q2 and P. Okay, so R2 is 5 meters. So the potential at point P relative to infinity is KE Q1 over R1 plus KE Q2 over R2. So we've got KE is 8.99 times 10 to the 9 Newton meters squared per coulomb squared times 2 microcoulombs over 4 meters, that's Q1, plus minus 6 microcoulombs, so there's a minus sign here, over 5 meters. So we have to keep track of the sign of the charges. But we have straightforward addition or subtraction, no vector math here. If you put that in your calculator, the potential at point P is minus 6.29 times 10 to the 3 volts, or minus 6.29.
The 3 is only used to find that 5 because Q2 we want to use a straight line to get to P?
Correct. Correct. You want the radial distance from this point. So you don't need to go through Q1 to get to P.
Yeah.
Yeah. Great. Good question. Okay. I'm going to go to the next page. So that's the answer to part A. I think you have a question like this on your homework. I think, for homework. Okay, I'm going to go to the next page now. All good. Okay. Okay. So we bring Q3 from infinity. We know that V of P is equal to minus 6.29 times 10 to the 3 volts. We know that V at infinity, we set it to be 0 for point charges. We made a choice there. That works well with our electric field equation and stuff like that. So it's 0 volts. So delta U is equal to Q3 times delta V. Because delta V is delta U per Q. Okay, so delta V is final minus initial, Vp minus V infinity. So it's just V at point P. So we have 3 microcoulombs times minus 6.29 times 10 to the 3 volts. Okay, so it would take nearly 2 times 10 to the minus 2 joules to bring a third charge of 3 microcoulombs to point P. Okay, and you can use this to kind of figure out any assembly of charges. So let's say we're figuring out the energy to assemble all of these charges here. So we've got a point P, and then we've got Q1, Q2, and Q3. When you bring in Q1, and it's the only charge around, there's no electrical work that needs to be done because there's no nearby charges. So when you bring in Q1 first, there's no work done in the physics definition of work. But when you bring charge Q2 in, Q1 is there. So you'd have to figure out the potential at the point where you put Q2, and then you bring Q2 in, and there's some delta U like we just calculated for Q3. And then to bring in charge Q3, you would do what we just did now, figure out the potential at point Q3 P, where Q3 is located. And the energy that is required to bring in charge 3 is part of the energy to assemble the whole 3-charge configuration. So there's no energy, no potential energy required to bring in Q1. There's potential energy required to bring in Q2 and potential energy required to bring in Q3. So you would add up all those contributions, 0, and then the U for Q2, and then the U for Q3. And that's the total energy you'd need to assemble all 3 of those charges in space like that. Okay? So we've just done one part of it. We've brought Q3 in to the vicinity of Q1 and Q2, where we know the voltage or the potential. So the energy to bring in just Q3 is this, but you can't figure out the energy to assemble all those charges. You just have to do it in steps. Okay? Does anybody have any questions there? Why we did that, how we did that? Okay.
I have a question, please.
Okay.
So if we were to take away charge from the potential field, would it be practically the same steps, but like flipped signs?
Yeah. So if you initially had these 3 charges here, you could figure out the energy required to disassemble the charges. So Q3, it would be like the opposite of the energy required to assemble it, to take it away. And the same for Q2. And then Q1 is by itself, so there's no actual, electric potential energy required to move it because there's no other charges nearby. Yeah. So it'd be the opposite. Yeah. Okay, because in that case, your final would be at infinity, whereas in this case, the initial is at infinity. So our signs get flipped around.
What does the negative joules mean?
It's related to the change in potential energy. So if you have a negative, like if the potential energy decreases, it means the kinetic energy increases. So you would have converted some potential energy into kinetic energy. The object would have some speed at the point it reached Q3. You would have to stop it when it got there, but to bring it in, it basically tells you that that charge Q3 feels a force of attraction to those charges Q1 and Q2, and it would happily come in that direction on its own. That makes sense?
Yeah.
Charges tend to get accelerated in the direction where their potential energy decreases. So it would feel an attractive force towards those Q1 and Q2. Okay. So let's move to the next part. These are all great questions. Like, they really get to the concept of this potential energy. So we have this idea now. We know what the voltage, like we just calculated voltage for a 1-point charge. If you look at these, if you look at this shape here, this represents those circles that we had for here. We have V is equal to KQ over R, and so V is a constant around a point charge at some radius, right? So there's a value of, VR here, there's a value of VR1 at this point here, or this is R1, I guess. So around a point charge, lines of constant potential are circles. And then when you put 2 charges together, then you add the potentials as just scalar numbers, and then you get a total potential field for the 2 charges present. So these black lines Those are the lines of constant V, okay? And these red lines are the electric field like they usually are, okay? Lines of constant V are perpendicular to the electric field because we only change the potential when we move along the electric field line direction. Okay, so we change from one constant V line to another constant V line, so there's a delta V along the direction of E. That's the definition we've been working with. In these diagrams, for potential, the closeness of the constant potential lines tell you about the steepness of the change of potential, and it's like a topographical map. So if you look at if you're into orienteering or something, if you look at a map, you can see that elevation, these lines of elevation, where they're really close together, that's where you have a very fast change in altitude or height. So we do the same for lines of constant voltage. So here, the change in voltage is pretty fast or pretty steep, and out here, it's not as fast. Our delta V happens over a longer distance. Okay? So it's basically the same kind of concept as these topographical maps, except we've got pluses and minuses thrown in, which obviously are pains in our necks as usual. So if we think about this as a topographical version of potential, negative charges are low potential or low voltage. Negative charges have low potential or low voltage, so they'd be a well like this, whereas high potential or high potential values are near positive charges, so you'd have a peak like this. So it's just like the topographical map, except we have minuses now. Okay. And this means before we had delta V is equal to minus E dot ds, right? We can reverse that integral and then use it to find, we can say, okay, delta V is the function of E through this integral, or we can say E is a function of V, but there's a derivative on the left-hand side. So basically, that's what we do. The slope of V, dV by dx or dV by dr, gives us the strength of the electric field. Okay, so this is basically the slope of V, or the rate of change of V as a function of distance, and then that tells us the electric field. Okay, so you can see here the lines of constant potential, the equipotential lines are really close together, but so are the electric field lines. So that's consistent. Where the electric field lines are really close, the electric field is strong. Where the equipotential lines are really close, the electric field is strong, and the rate of change of the potential is really high. Here we have constants. We have a constant electric field, and then here, and then we have constant lines of constant voltage that are straight lines also. So as a charge moves through this region, it sees a constant rate of change of voltage as it moves through this constant electric field region. Okay. And as a charge might move away from, a point charge, it will see lower and lower electric field values. So it experiences the change in potential of some constant amount over a longer distance. Okay, so if this is 5 volts, 10 volts, 15 volts, 20 volts, the further you get away, the farther you have to go to reach, to go through the same number of volts over a distance. Okay. If anybody has seen this before, just for your interest, this can be written as the gradient. So anybody, don't worry about this, but anyone who knows what the gradient is, that's how you relate the electric field and the voltage in 3 dimensions. But we will, in this class, look at basically these kind of configurations where we can do the derivatives in 1 dimension. Okay, so we look at the rate of change of V to tell us what E is. Okay, has anyone got any questions there? Okay. All right. So if we want to be able to find if we want to be able to find E from V, then we have to be able to find V from the charge distribution. So we're going to have to do one little more bit of integration here, and we'll try and do a straightforward example here. But basically, given some charge distribution, okay, it's made up of little elemental bits of charge, which all, create a potential at some point P. We've got R3, R1, R2, and they're related to little elemental bits of charge in the source object, charged object. So what we want to do is to add up all the contributions from all the little elemental bits of charge at some point P. Okay, so we're using the point charge version of this equation. We're going to treat all of these as little point charges and add up all of the little bits of voltage from each of the little bits of point charges at point P. Okay, so let's do an example here. We've got a ring of charge here, and we want to figure out, and we can think of the ring of charge as a whole bunch of little DQs going around in a circle. Can you see where I'm drawing here? So we've got a whole bunch of little DQs. R is equal to a constant, okay? So it's a ring of radius of charge of radius R. And theta, if we run around this whole circle, theta goes from 0 to 2 pi, okay? So what we need to do is to set up our little DQ and then add up all, or integrate over all the little contributions as we swing through this full ring of charge. The ring has radius R, and that means that every point on the ring with little elemental charge in it has the same distance to that little bit of elemental charge on the ring. So Z is fixed, and then this distance from point P, the hypotenuse of this triangle from point P to the ring charge, is this value here, okay? And R is fixed and Z is fixed here. So the only thing that we need to change is theta. We're going to take that triangle and rotate it around so we get all of the contributions, and these are the R's in our voltage equation. So we've got our little DQs here, and then the R is this distance from the ring to the point P. Does that make sense? I hear silence. Okay, I'll assume we're okay for
Wait,
now.
could you go back for 2 seconds? I was reading.
Yeah. Okay.
So Z and R are both constants, and then that makes the small r a constant as well.
Correct.
It's just the DQ that's changing.
Correct. Yeah, and the DQ, I'll show you on the, are we ready to move? I'll show you what, I'll write this out a little bit better for you.
Yeah. Yeah, I'm ready.
And we have a line charge lambda. So it's coulombs per meter around this ring. Okay. So we've got, let's just draw it out a little bit better here. So we've got
Sorry.
our ring.
What does the lambda mean?
Lambda is linear charge density. Density in coulombs per meter. So there's so many coulombs per meter around this line charge. So it's like a wire that's in a loop configuration. Does that make sense?
Kind of, yeah.
Kind of, yeah. So we don't have like a surface charge. It's not a, coulombs per square meter or whatever. It's just a little bit here. Okay. So we've got R, we've got theta, we've got Z, we've got R squared plus Z squared, And this is our little DQ. So we need to take, we have charge per unit length. So we need a little elemental length here. And if you remember from, hopefully this is from high school, but if you have a circle of radius r and an angle theta, the arc length of this piece is r theta, right? Hopefully that's known. For our case, we have a little tiny angle d theta. So the arc length then becomes r d theta. Okay, so that's the length of this little bit of the circle that's, within that angle d theta. So our dq is our density times our arc length. That's how you get dq. Does that make sense? Maybe not. So this is line density. This is.
So that's just at that point. So if you wanted to do the whole thing, you just integrate over the whole ring.
Exactly. I'm so excited that someone said that. Sorry, I didn't see who said that, but yes, exactly. So we want to do all these DQs all the way around. So we're going to integrate from theta equals 0 here all the way around to 2 pi to catch all of them. That's what the integral does. Okay, it sweeps around through that ring and adds up the contributions of all of it. Okay, great.
Will we ever have to know, because this one says to use lambda, would we ever have to just figure out which one to use, or will it always tell us?
Well, in real life, if you ever had to do this, if your real life involved this, you might not be told this, but in this class, we would tell you that it's lambda.
Okay, good. Yeah, because I have no clue.
Yeah.
Yeah. Okay.
Yeah,
Good.
because we would give you the variables that we want you to get the answer in, so that we could, mark it. So it's easier for us if we tell you what the variables are. Okay. You do need to know that it's a linear charge density. It's a thin ring. It may have even said that, but yeah, linear charge density lambda. Okay, so let's try and get done this. Oh, we're getting over a little bit over time. My apologies. Okay, let's finish this up. So we've got V is equal to KE. So V, for a 1 point charge, we have V is equal to KEQ over R. Okay, that's for 1 point charge. But for this ring, we've got all of these little DQs that we've got to add up. So we're integrating over all of these little DQs, but we can replace that with things that we know. So we've got lambda R d theta, that's our DQ. And then the actual radius is this distance here. This is equal to R for our voltage calculation, because this is the different distance between the charge and the point P. That's what the R is in the potential formula. Okay, so we're going to substitute that in. Okay, and this is a scalar, so we don't need any unit vectors, thank goodness. This is a constant, this is a constant, this is a constant, this is a constant. We integrate from theta equals 0 to 2 pi. So let's bring out all these constants. Okay, so the integral of theta is just d theta, or sorry, the integral of d theta is just theta. So it's 2 pi minus 0, so it's just 2 pi. Okay, so these are the limits of our integration. So are we okay with that?
Isn't lambda times like the total distance just like the total charge?
That is correct. Well, it's actually 2 pi r. That's the total length. The circumference of a circle of radius r is 2 pi r. But yes, lambda r combination is related to the total charge.
So could we make like our own equation for that instead of integrating, if we could make that generalization?
If you understand that the like the symmetry and can explain it in words, you can do that.
So if I could draw like in a picture like 2 lines and then I cross out my x's and just keep my z,
Mm-hmm.
then I could make that generalization.
You'll need to like start here where I'm drawing up at the top and tell me how you get to the end, but you can rationalize it.
Okay.
Okay. So we got V is equal to 2 pi ke lambda r over square root of r squared plus z squared, where 2 pi lambda r is the total charge. Okay. Anyone got any questions there? I think you got it. It feels like this is not as terrible as the electric field version of this was, because you might have done a little bit of math since then too. And this is also scalar. Okay. So here's the answer that we just got. It uses ke is equal to 1 over 4 pi epsilon naught. So it's replaced ke by that, but it's the same thing. If you look at really far away distances, you basically get the potential. Like if you're really, really far away from the ring, it looks like a point charge. Okay. There's another example in the book, and I'm not going to go through it, but I want you to just take a look and read through it. It's the same thing, but it's a disk. So in addition to theta going from 0 to 2 pi, we have r going from 0 to r, capital R, the radius of the disk. So it's a slightly more complicated setup, but it's the exact same principle that we've done. We basically integrate over a bunch of concentric rings. Okay.
Could you go back
Can you
to
show me the
integration slide? Thanks.
Mm-hmm.
So we just plug the 2 pi back into the equation there after integrating it?
So you go here. Yep.
Okay.
Yep. Okay. All right. That's all we're going to do for today. So thanks very much, everybody.
Thank you.
Thanks.
Thank you.
Have a good day.
Sorry, so how do you know that 2 pi lambda r is the total charge? Like, do we have to know that, or that's just like something that you realize?
If you have a circle, let's look at this from the top. And we have a line charge density that is equal to, or like the units is coulombs per meter, then the total charge is the line charge density times the total length of the bit of charge, right? So the total length of a circle of radius r is the circumference of the circle, right? So Q is equal to lambda times the circumference of the circle, which is 2 pi r. Does that make sense?
Yes. More or less.
Yeah, you have to know that this is the total length. So if you want to find the total charge, you need the charge density in coulombs per meter times the length in meters.
Yeah.
Yep.
And then if there's ever times where we don't use lambda, because I know I don't remember them specifically because last week's stuff was really confusing to me, but I know that there was different ones.
Yep.
Would that replacement for lambda it'd be the exact same equation just with that variable in its place?
Yeah.
Like in that whole equation?
Yeah, sigma is coulombs per meter squared. So if this was a solid circle, you'd need, like, the total charge is sigma times the area of the surface. So then you do sigma times the area of this circle is pi r squared. Okay? For a surface. And then there's a rho, which is coulombs per meter cubed. So total charge will be rho times volume. So it's rho times 4/3 pi r cubed for a sphere, for example.
Oh, so that would change the equation a little bit then?
Does change the equation, yeah. So in question 7 on assignment 1, it had a surface charge sigma, but the question was really close to one we did in class with a line charge lambda, but it's not the exact same equation in the end, although the method is really similar, formula is slightly different. Yeah.
Okay.
Yeah, and this other stuff would be a little bit different too, because you'd have to integrate over the whole shape. We just integrated over the line charge, so that was a simple 2 pi term.
Oh, so that equation for that part, okay.
That equation changes as well, yeah.
Not just a simple line, okay.
Correct, yeah. Yeah. Yeah, so this, if you had a different type of charge distribution like the disk, this whole front part changes too.
Okay.
I was just wondering if solutions to the written questions on the assignments will be posted at some point.
Yeah, I just have to get to it today. I have written solutions for all the questions, including the WebAssign ones, and I'll post them today.
Oh, okay, thank you.
Yeah, you're welcome.
Is the test still supposed to just be 3 questions, or is that changed at all?
It depends on the types of questions, I guess. We're going to try and set it up. The length of the test, we're going to try and set it up so it's doable within the time of the test. So that may be 3 questions or 4 questions, depending on how difficult they are. But I'll let you know before there. I haven't set up the questions yet. I've been working on the lectures. So, yeah.
So if it's like
circuits part 2.
What's that?
Last term, our circuits module test was not very fun.
Oh yeah, they made it really, really long, and it was very hard to finish in the time.
We'll try not to do that. I mean, at this point, kind of who knows sometimes, but we'll try very hard not to make it.
It is what it is, honestly.
Yeah. We'll try to make sure that we put questions on there where we can evaluate your understanding of the concepts and try not to make the math too difficult. If that makes sense, So like assembling charge configurations, how much energy does it take to do that? That might be a good question, because there's like, you don't have to set up an integral like this, stuff like that.
Mm-hmm.
But it does test your knowledge of, the change of potential energy and the change of the voltage.
Yeah, and so like, I know you said you don't know if it's 3 or 4, but like technically, if it was 3, it'd be 1 question from each of the 3 weeks for this unit.
This unit is 2 weeks plus 1 day.
Oh, okay.
It's 7 lectures. So I'm finished. Monday's my last day, and we're quite a bit behind right now. So we'll see how far we get. Monday's the last day for this module, and then Professor Kudel takes over on Wednesday and does 7 lectures himself, and then Professor Tui takes over and does 7 lectures. Because of the late start, we
very
have
fast.
Yeah, we're having a meeting with that first year engineering today to say this is too fast.
Yeah,
very much
because
too fast.
Like, because it's so fast, I know personally I hardly understood anything from last week.
I know. Yeah, and I can see like accelerated delivery, like focusing on that topic is okay, so long as they free up time in your schedule to actually do that. But you guys have full schedules, like all day is booked.
Yeah.
That doesn't work. So we're having a meeting with them today. That's why we're trying to kind of adjust on the fly, so things aren't going 100% smoothly, but hopefully we get there. I think once you get out of this section, the math isn't quite as bad. For some reason, you have the hardest math right up front too.
Like, you mean like the magnetism part's less confusing math?
The magnetism part is more multiplication. There's a cross product in there, but
super weird considering we're just learning this stuff in math.
Yeah, there's not these big giant surface integrals and volume integrals and all that sort of stuff.
I'm pretty sure they did the same thing to us in dynamics last term with our math class.
Yes, they did.
Like,
You know
I'm pretty
what?
sure it's the exact same thing.
Yeah, you know what? You should really tell, like, where you have the opportunity to give feedback to engineering, please tell them. We will tell them too.
We actually did throughout our classes. We kind of like that's why like our computer science class went a little differently, and I'm pretty sure circuits the test was graded differently because of the way it went.
Mhm.
Yeah.
Okay. Yeah. Yeah, we're not sure what to do. Like, we're teaching you out of a standard first year engineering textbook that's used across North America. So we want you to be at that level, but the way that the program is set up, it doesn't quite get you there. So that's not great. But I mean, anyone who goes into, you know, EP or electrical, you will get review in year 2. So, you know, you'll get there. And you have to see this stuff a lot of times. I think I didn't understand Gauss's law, really what it meant, until maybe 4th year university, and I was in physics, engineering physics program. So you have to see it again and again and practice it, which also doesn't help with accelerated delivery because you don't have time to practice again. Yeah.
That's a bit more reassuring though, because I know I don't get it.
Yeah, well, yeah. Charge creates electric fields, and then you count them coming through a surface. That's basically what you gotta know. But you gotta get used to it, because you don't usually think that way. You don't usually count lines passing through surfaces. So, yeah.
Exactly.
Yeah. Yeah.
Can I just ask one quick question about the assignment again? Sorry.
Yep.
So is it okay? Like, I know you said at the beginning that we have to make sure we click through the links to get our assignments graded. Is it okay if we go through WebAssign? Just because the assignment 2 link is giving me, it's just saying it's an unpublished module or something. But I can find the assignment through WebAssign if that works.
You should be able to see it. I'll go into WebAssign right now and make sure that it's published at the right time. We were having some trouble with the integration with Canvas, so I'm not sure if the problem will be in WebAssign or Canvas, but I'll fix it. I'll fix it right after I'm done with talking to everybody here. Okay?
Okay, thank you.
Yeah, you're welcome. Thank you for letting me know. Is that all we got for today? Does anyone else got anything? Otherwise, I'm going to go into WebAssign and see if I can figure out what's going on in there. Cool.
Hello.
All right, thanks, everybody. Oh.
Hello. Do you want to go over question 7 from last week and like do it?
I'll
Show me how
post
to
this
do it.